everyone, we're Team 7 and our topic is data-driven control of exoskeleton for optimal lifting task assistance. Here's the overall content of our presentation. Our project is about exoskeleton. Exoskeletons are wearable electromechanical devices that aim for the following goals: enhancing the physical performance of a wearer and to provide guide rehabilitation or locomotion assistance. This project is based on this paper, a data-driven reinforcement learning solution framework for optimal and adaptive personalization of a hip exoskeleton by Tu and others, published in 2020. The goal of this project is to provide optimal and adaptive personalized talk assistance for reducing human efforts during walking and to develop a novel data-driven solution framework based on reinforcement learning. This project also aims at designing a controller to tune assistive torque profile of the hip exoskeleton that coordinated with human actions and reduce activation level of the hip extensor muscle in human. Here's the hardware model that we are trying to work on. We have found a related work on hip exoskeleton, effect of hip assistance level on human energetic cost using robotic hip exoskeleton by Kang and others. This hip exoskeleton has 2 degrees of freedom and weighted around 7 kg and actuated by 2 series elastic actuators with peak torque of 60 Nm. For the related work in control aspect, there is a hybrid control of the Berkeley lower extremity exoskeleton, which includes the high and low level layers. The high level is responsible for estimating the guide phases of the wearer, while the low level controls torque or force. Another control approach is impedance or admittance control. It is a compliance-based control method that can produce the complementary portion of torque necessary to complete a compliant movement of the wearers. The integral admittance shaping algorithm was proposed to control the robotic hip exoskeleton in the research of Nagarajan and others. In the paper that we used as a reference, LSPI algorithm is used for prediction. This algorithm is a reinforcement learning algorithm that extends the benefit of LSTD algorithm to control problems to be used without a model, which is the case for most RL-based control problems. In order to implement LSPI, we have chosen to use RLPY library. This is the Python library targeted for conducting sequential decision-making experiments, and it includes the LSPI algorithm in one of its default agents. This can reduce our workload and we don't have to declare new agent ourselves. We have successfully applied the LSPI sample program to an RLPY library. The task given to the program is moving from the starting position to the ending position without touching the prohibited zone. The code could complete the task after the learning process. However, until now, no self-defined class is used and only the classes given in RLPY library is used. This means that the LSPI algorithm that we're currently working on is not for our exoskeleton. The problem that we discovered while developing with LSPI will be further explained later.
Hi, I'm Usman and I'll be continuing the project presentation. Okay, so previous application plan. Our previous application plan, as was given previously, was that we would improve the code and implement it into the physical system that is our 1 degree of freedom exoskeleton, hip exoskeleton of TSA based. So due to the given circumstances of the 3 group members not being in the same country, we weren't able to implement the improved code into the physical environment. So instead, we changed that into the execution strategy that was to create an environment on the MATLAB similar to the TSA dynamics of our system and implement the improved code onto that to see the results. So this was the execution strategy that we came up with. We created an environment on the MATLAB similar to the dynamics of the TSA-based exoskeleton of our 1 degree of freedom and implemented the improved code onto it to get the results. So coming on to the improvement approach. Okay, so we chose DDPG over LSPI as an improvement code. So what is DDPG? Basically, it is a model-free off-policy algorithm for learning continuous actions, and it provides the maximum reward. So basically, it has 2 networks. One is the action network that takes in one input of state and provides an action. as output. Then there is critic network, deep critic network, that takes in two inputs, that is a state and action, and provides an expectation, maximum expectation of the reward. And overall, the DDPG finds the maximum reward and provides such states that finds the maximum reward. So why we chose DDPG over LSPI? So as was shown in the previous presentation, we did LSP and DDPG on model test data, and we got these results. On the left side, you can see the LSPI result, although it showed a much better performance as compared to DDPG, but DDPG was a much faster and easier solution because in 100 episodes, the DDPG provided a converged data. Meanwhile, LSPI took 1,000 steps. So for our 1 degree of freedom exoskeleton, hip exoskeleton, DDPG is a much easier and a better solution overall. So coming on to the creation of the DDPG algorithm. So first of all, we created an environment. In the environment that replicated the TDSA-based exoskeleton dynamics, which will be explained later on. Okay, so we first chose the observation as 1. The observation was of tracking error, that is the error between the current value of angle of motor minus the angle of the desired motor angle. So overall, the observation, that is the state, is 1, and meanwhile the action was taken as the gain of PD controller. So it was kept between 5 and 20, and meanwhile the DDPG can find the optimal PD gain for our solution. Okay, so coming on to the reset function. The reset function is basically required for resetting the states back to 0 after every step. So we designed the reset function as follows, as given in the picture. Coming on to the active and critic network, as was briefly explained previously, these are the properties. So active network, it takes the observation and it returns the action that maximizes the long-term reward. Meanwhile, the target actor just improves the stability of the optimization. Critic does the same, but it takes two inputs as observation and action and outputs the maximum expectation of the long-term reward. And while the target critic improves the stability while updating its parameters to the critic parameters. So coming on to the DDPG algorithm of actor and critic network, we designed the actor and critic network as follows. On the left side, you can see the critic network that utilizes 3 layers and 4 layers in total, 3 layers for the observation input and 1 layer for the action input, and it combines them and provides the output. Meanwhile, the actor network just is similar to the critic network. It just utilizes 3 layers for the observation and provides 1 output as action.
Hello everyone. I'm going to explain about our result. So in the first time, we plan to control the hip joint exoskeleton, which is controlled by the TSA system. But instead of controlling overall system, we try to control the TSA-based lumbar system, which is linearized outputs of TSA. It can be used for lifting a system and also can be used as haptic device. To control this system, we need to solve the nonlinear property of the string itself. So when the string is twisting several times, it has a creep and the nonlinear characteristic behavior. So we try to solve this issue with our new control algorithm. To perform this experiment, we analyzed the system behavior, then what is the problem. So we found that even though we are controlling the motor side joint angle, this is not correctly related with the output position, which means that whenever we try to control the system, the output location and string property get different. We found this problem that maybe this is the reason why the radial string is changing and length of the string is also changing. And it relates to the initial zero twisting point distortion. So we try to overcome this issue with the DDPG algorithm because the reason we are facing on problem is randomly changes. So even though it has a random changes happen, if we are properly provide the control algorithm, then we can overcome it. So this is the overall dynamics of the system we propose, and we get this parameter with the analysis of our number system and try to uh, learn in the dynamic system and dynamic programming. We also get the entire error over the system is dynamic algorithm and dynamic simulation is running. And this is the overall result what you get. So at first we set the random string radius and length value and over the time and try to control the PD control with our system and also optimize the PD gain. So with the optimized PD gain, we perform the evaluation of our system and get the following result. So tracking error is extremely small and control top, which means control effort, is also small. We try to minimize those error and the control effort with our optimization technique. Uh, but we have to compare with the DDPG based result and our optimization technique. But unfortunately, the DDPG result show us the very poor performance as compared with the just KP optimization. But it's still okay to get the good result. So result of the KP gain is 3.4. So this is the overall result what we got through this semester.